You're listening to AI Papers, a deep dive. We take a single new paper and unpack what it says, why it's novel, and where it breaks. Let's jump right in. 2 weeks. That's how long DeepSeek ran its newest flagship model before they tore out the part that makes it generate text fast and bolted in something new. The replacement makes each user's words come back 60 to 85% faster on the same GPUs, serving the same number of people at once.
Quick heads up before we get into it. This is an AI-made explainer, both voices included. And that pairing is the part that should bug you, Cassidy, because faster per user and same number of users usually trade against each other. You speed one person up by handing them more of the machine, which means fewer people fit.
Right, and the system that breaks that trade is called DSpark. By the end, you'll understand the two moves it makes, and the strange one is this. Their faster drafter is, in one sense, the dumber one. It guesses a whole run of words blind, none of them looking at each other, and it beats the careful model that reads each word before guessing the next.
Which sounds backwards. And it matters past DeepSeek's data center, because the thing slowing down every chatbot and every agent isn't how much math the chip can do. It's that the model is forced to write one word, write the next. Whether you can serve fast responses to a crowd comes down to beating that.
So start with why it's slow at all. A language model writes one token at a time. A token's roughly a word-ish chunk. To produce each one, it rereads everything written so far and does a full pass-through itself. A 500-token answer is 500 of those passes, each waiting on the last.
And the cruel part is the hardware. A GPU is built to do thousands of things at once, but that one-at-a-time chain means it does one small thing, sits idle, does the next. You're paying for a parallel monster and using it like a typewriter.
The fix everybody already uses is speculative decoding. Picture a fast junior assistant and a senior expert. The junior drafts the next several words in a blink. The expert, the big model, reads that whole draft in a single glance and checks it, which is exactly the cheap bulk work a GPU's good at. Whatever the expert would have written anyway, you keep. Guess right, you got several words for the price of one expert pass.
And there's a piece of math underneath, rejection sampling, that makes it exactly lossless. The accept or reject rule on each token is rigged, so the final text carries the identical statistical fingerprint the big model would have produced on its own. Free speed, no quality cost. That's the foundation, and DSpark doesn't touch it.
It builds on it. And the open question the field's been chewing on is how to get that junior drafter to propose longer, better runs of words, because that's where the speed-up lives. Here's where it's split into two camps that each got it half right. Camp 1, auto-regressive drafters. The junior writes one word at a time, each seeing the ones before it. Coherent, but sequential, so it has to stay shallow and short. Camp 2, parallel drafters. Fire out the whole block at once, every position guessing independently. Nobody seeing what their neighbors picked. Fast, can be deep, but the guesses don't coordinate.
Uncoordinated how? Like the words just don't fit together?
Exactly that. The paper's own example. Say the next two words could be, of course, or no problem, both fine. Position 1, hedging across the options, picks of. Position 2, independently, picks problem. Each made a reasonable local call, and you get of problem. Nonsense because the two positions never agreed on which phrase they were building. That's multimodal collision, and it's why a parallel drafter's accuracy crumbles after the first couple of tokens.
So the obvious scoreboard says auto-regressive wins. Coherent beats incoherent. Slower, sure, but at least it isn't emitting of problem.
That's the conventional wisdom, and when DeepSeek actually measured it, the parallel drafter won. That result is the hinge the whole architecture turns on. And it took a new way of measuring to even see it. Here's the measurement they invented. Call it position-wise conditional acceptance. For each spot in the block, ask, given that every word before it was already accepted, how often does the word at this position survive the expert's check? That separates how good the drafter is at position 4 from the fact that positions 1 through 3 might have already tanked.
And on screen, this chart is the heart of the paper: acceptance against position. Walk through what the two curves actually do.
The parallel drafter starts way up high at position 1, much higher than the auto-regressive one, because it can afford to be deep and smart there. Then it decays fast. By position 4, it's rotting. The auto-regressive drafter starts lower but stays flat, even drifts up. Two very different shapes, a tall cliff versus a low plateau.
And the cliff wins because of the relay race logic. It's a strict prefix.
That's the key. Speculative decoding accepts the block as a prefix. The instant one token is rejected, everything after it gets thrown away, however good it was. It's a relay where if the first runner drops the baton, all the downstream effort is wasted. So position 1 carries enormous leverage. A drafter that's excellent at position 1 and mediocre later beats one that's evenly okay, because that first leg decides whether you get anything at all.
So the parallel model's first token firepower dominates even though its tail rots. The fix writes itself. Keep the deep parallel backbone for that position 1 strength and find some cheap way to stop the tail from rotting.
And cheap is the whole game. That's the semi-autoregressive design. Keep the expensive work fully parallel. The backbone spits out a first draft set of probabilities for every position in one shot, capturing everything except coordination between words. Then a tiny sequential head walks left to right and adds a correction at each position based on what was actually just sampled. Back to of. The head's job is to learn that once position 1 landed on of, position 2 should lean course, not problem.
So it's the two people finishing each other's sentences. Except now person 2 gets to glance at the word person 1 actually wrote before committing.
Precisely. And the cheap version, the Markov head, is basically a lookup table. Given the previous token, here's a little vector of nudges to reweight what comes next. They keep it low rank, so even with a 100,000-word vocabulary, it stays tiny. Which matters because if the sequential part got expensive, you'd have thrown away the whole reason you went parallel.
And there's a constraint that killed earlier attempts at this, right? People have tried to fix parallel incoherence for years.
They have. And most of those fixes are illegal here. Old parallel coherence tricks use global normalization or marginalize over hidden variables. And that wrecks your ability to read off an exact probability for each individual token. But the rejection sampling rule needs exact per-token probabilities, or the lossless guarantee collapses. DSpark's trick is staying strictly local. Each correction depends only on the actual previous token, so clean softmax probabilities survive. It's shaped as much by what's mathematically permitted as by what's smart.
So how much does this sliver of sequencing actually buy you?
A 2-layer DSpark beats a 5-layer pure parallel drafter across every domain they tested. A little token-to-token memory does more than stacking parallel depth. Against the auto-regressive Eagle 3, accepted length climbs around 27 to 31%. Against the parallel backbone it builds on, 16 to 18. And the overhead is almost nothing. Pushing the draft from 4 tokens out to 16 adds between 0.1% and just over 1% to the round trip, while delivering up to 30% more accepted tokens.
Because the expert's verification pass dominates the compute anyway, so the little head rides for free.
Right, that's Act 1, draft better. But there's a second bottleneck, and it's the one that actually killed their last production system.
Worth flagging one thing about those numbers before we move on, though. Every figure Cassidy just gave, the accepted length gains, comes from tests with the scheduler switched off on Quen and Gemma models to isolate raw draft quality. The 60 to 85% production win comes from the full system on DeepSeek v4. Hold on to that gap. No single experiment shows the whole machine end to end, and that comes back to bite later. Here's the formula that organizes everything. The latency for each token you actually keep is the draft time plus the verify time divided by how many tokens got accepted. 3 knobs. Draft faster, draft better, that's the bottom of the fraction, or make verification cheaper. Act 1 pushed on draft better. Act 2 goes after the verify term, and that's where this turns into a systems paper.
And the naive move would just be verify everything the drafter proposes. Longer drafts, more free tokens.
That's exactly the move that blew up on them. Verifying a token isn't free. It occupies batch capacity. Under light load, checking an extra speculative token costs basically nothing. The GPU's got room. Under heavy load, that extra check is capacity you just stole from another user in the queue. So a long, aggressive draft that's a clear win for one person can drag down throughput for the whole crowd.
That's the throughput versus latency tension. Throughput is how many people you serve at once. Per user latency is how fast your own answer feels. Long drafts buy the second by spending the first.
And that's why DeepSeek's previous production setup was the most timid thing possible: a single token drafter. They tried more aggressive static drafters and shelved them because at high concurrency they strictly hurt throughput. They left speed on the table on purpose. DSpark's second idea is to stop treating draft length as a fixed dial and make it a live, load-aware decision.
So picture express lanes that open and close with traffic. Quiet server. Verify 5 or 6 tokens per user, nearly free. Server slammed with concurrent requests. Shrink the budget back so those checks don't rob everyone else. Same instinct as opening highway lanes off-peak and closing them at rush hour.
And to make that call, it needs 2 things: a guess at how likely each draft token is to survive, and a read on how busy the hardware is. The first comes from a confidence head, one small layer that outputs, per position, the chance that token survives given all the earlier ones did. Those estimates have a known flaw, though. Neural nets rank well, but run overconfident. The head can correctly tell you token A beats token B while claiming 95% when the truth is 80. Raw, it was a good ranker, discrimination in the low to high 80s. But its calibration error ran 3 to 8%. So they tune it with a single dial, temperature scaling, that softens the inflated numbers until they match reality, dropping the error to about 1%. The scheduler has to trust the magnitudes, not just the order.
Now the scheduler has trustworthy survival odds for every candidate token across every user in the batch. And deciding how far to verify each one looks like a brutal combinatorial problem. But it collapses into something almost embarrassingly simple. And the reason it collapses hides a correctness trap that, when they fixed it in production, accidentally made the theory more correct, not less. That's the next stretch, the densest part, and it pays off in that twist. Start with why it's simple. Extending any draft can only lower its cumulative survival odds. Each extra token is one more chance to fail, multiplied onto the running product. So the value of adding any one token is just that token's own survival probability, which means you don't reason about whole blocks. Throw every candidate token from every user into one pile, sort by survival probability, and admit from the top down, like boarding the passengers most certain to actually fly first, until adding the next one would slow the plane enough to hurt total throughput.
And hurt throughput isn't a guess. They profile the engine once at startup, a little table of how fast it runs at each batch size, and read the trade-off straight off it. Total throughput is expected accepted tokens times steps per second at the current load. Greedily admit, stop when that product peaks. But here's the trap Cassidy flagged. Speculative decoding has to be non-anticipating. Your decision to verify token K can't depend on token K's own value. Peek at the token to decide whether to check it, and you've leaked information that breaks the lossless guarantee.
And the bet analogy is the cleanest way in. Judging whether to make a bet by peeking at whether it happened to win, instead of the odds when you placed it, is cheating. The confidence head computes the next survival odds using the token that was just sampled. So a retrospective sort across the whole batch could let a token's own outcome sneak into whether it gets admitted. The appendix has a clean case where that bias drags a true 70-30 output distribution to 85-15, no longer lossless.
In the clean algorithm, the early stop break saves you. It halts before it ever evaluates anything that depends on the peeked-at token. Causality preserved. Then they deployed it, and reality was messier. The clean argument assumes a smooth capacity curve. Real GPU capacity is jagged and stepwise. And worse, the scheduler needs the next batch size before the current step even finishes, a hard constraint of their zero overhead scheduling. Their fix: approximate the load using confidence outputs from 2 steps earlier. Stale data.
And here's the twist. The stale data fixes the causality problem for free.
It does, because the admission decision now depends only on already finished history, outcomes fully realized 2 steps ago. A token's own value can never leak into the choice to admit it. The shortcut everyone would assume degrades correctness is the exact thing that restores it. A practical compromise that makes the theory cleaner, not dirtier.
So where we are. Act 1 made the draft coherent without paying the autoregressive tax. Act 2 spends verification budget only when the hardware has its spare. Put both in front of real traffic. What happens?
If the load-aware story is right, you'd predict the verification budget should breathe with traffic, wide when it's quiet, tight when it's busy. And that's exactly what the telemetry shows. From the old static 2 tokens out to 4 to 6 per request under light load, smoothly shrinking as concurrency climbs. The per-user payoff: 60 to 85% faster generation on V4 Flash, 57 to 78 on V4 Pro, at matched throughput against the single token baseline they replaced.
And the reason adaptivity earns its keep: how many tokens you can safely draft swings hard by task. Structured work like math or code, the drafter nails long runs, around 5.5 accepted tokens. Open-ended chat is choppier, closer to 3.5. On chat especially, turning up the confidence threshold to prune the doomed tail tokens lifts the acceptance rate from about 46% to 96%. A static budget can't track that swing. A load and confidence-aware one can.
The cleanest way to see the whole thing is the Pareto-frontier, that menu of best trade-offs. Throughput on one axis, per-user speed on the other. Every operating point you could pick sits under one curve. DSpark's curve sits outward and to the right of the baselines. Strictly more speed and more users on the same hardware. That's the honest headline. A better menu, not one magic multiplier. And I want to flag a number the paper itself disowns. At the very strictest latency targets, the charts show throughput gains like 406%, even 661. Read as a 7 times speedup, that's wrong, and the authors say so. What's actually happening is the old baseline falls off a cliff at those strict targets. It can barely sustain a tiny batch, so the ratio explodes against a number near 0. The real claim is the cliff itself. DSpark keeps running where the old system simply couldn't. And that honesty is the right note to get critical on, because the paper has a real soft spot. Remember the gap I flagged? The offline quality numbers run with the scheduler off on Quen and Gemma. The big production numbers run the full system on V4. No single experiment isolates the scheduler's own contribution on reproducible public models against a strong competitor. You're asked to trust that the two halves compose, and that link is asserted more than it's shown.
That's fair, though the production deployment is unusually real evidence. This isn't a benchmark with one request at a time. It's serving live traffic at scale.
It is, and that counts for a lot. But look at what it's compared against. A single token drafter, the most cautious setup possible. They admit they never deployed an aggressive static multi-token drafter because it hurt throughput. So part of DSpark's win is over a deliberately timid baseline, not a well-tuned aggressive one. And the deployed scheduler isn't even the clean algorithm. It drops the early stop, uses stale estimates, and runs on that jagged capacity curve the optimality argument assumed away. So the thing in production is a heuristic whose optimality is shown empirically, not guaranteed. It clearly works. But it works in our data center, and we proved it's near optimal, are different claims, and the paper sometimes lets them blur.
I'll grant the blur, Tyler. What I think they've earned cleanly is the reframe. And there's one more thing they were honest about, the RNN head. They built a fancier sequential head too, one that carries memory of the whole prefix instead of just the previous token. It was pitched as the more powerful option, and it barely beat the simple lookup table, mostly at long blocks, so they dropped it from deployment. Honest to report, but it means one of their two architectural bets didn't earn its place. But step back to the durable idea, because it outlives this one system. Two reframes. First, the place draft model capacity pays off most is position 1, first token leverage, and a sliver of token-to-token memory is enough to save the rest. Second, and bigger, how aggressively to verify isn't a setting you tune once and forget. It's a live decision the server should keep remaking as load changes. That second idea is the one other inference systems will borrow, whatever happens to DSpark itself.
And that points at the one cost DSpark still can't dodge. It always pays to draft that first block through the parallel backbone. And for a genuinely hard query where almost nothing gets accepted, that compute is just burned. So here's the split I'd put to you. Is the future more of this? Serving systems getting ever smarter about spending a fixed draft budget across a crowd? Or does the real next gain come from refusing to pay that upfront draft cost at all, on the queries a model can already tell are hopeless? If you've run inference at scale, you probably already lean one way. Say which, and why.
If you want to go deeper, the full annotated version of this episode is on paperdive.ai. Every term tapped to define, with links to the related papers grouped by theme, plus the weekly and monthly roundups.
Quick housekeeping. This script was written by Anthropic's Claude Opus 4.8. Cassidy and I are both AI voices from 11 Labs, and the producer isn't affiliated with either company. The paper is DSpark, out today, June 27, 2026, from DeepSeek and Peking University. The trick was never just drafting more. It's knowing when the road's clear enough to open the extra lane. See you in the next one.